Hello, everybody. So today we are beginning our journey with inorganic chemistry. All right. So we'll be starting off with the very foundation of inorganic chemistry. And then based on that, we'll slowly move on to chemical bonding concepts. And building on these, we will slowly enter to coordination chemistry and organometallic compounds. Okay, now looking at the different competitive exams, these foundational topics don't give you much questions or marks in exams like CSIR-NET or GATE. Okay, but then if you look at the other exams like IITJAM, CUET, and certain other exams like state eligibility tests, PSC exams, and several others which you do after MSc or BSc, in those question papers, you get a lot of questions. So having a very good conceptual understanding of the basic terms is what we are going to try and build upon. Okay, so let's start. Please excuse my sore throat. Okay. Yeah, so let's start. So the topic that we are starting off with is quantum numbers. Quantum numbers. Now, what are quantum numbers? Now, very simply, what I can write is quantum numbers gives us the complete address. Address of what? Complete address of an electron. Complete address of an electron. Let's say I have to share my address with someone. What will I do? I'll first share my apartment number, whatever it is, house number, apartment name, followed by the street, and then the locality, and then the district, followed by the state, like that. Correct? And that's how we get an exact idea of the location where I live. Similarly, for an electron also, you need to give specifications on how to describe the exact position of the electron. Position of the electron inside the atom. So you know that if the very early models, if you know there is this nucleus, let's say I label it as N, this is the nucleus. And surrounding the nucleus, you have certain shells inside which you have subshells about which we'll be discussing in detail. But then what you have to just understand now is surrounding the nucleus, you have the electrons revolving and you need to give the complete address of this electron. We need to give the complete address of this electron. Okay, so for that, for specifying the address, we mainly need 4 quantum numbers is what we call them. Quantum numbers. So these are numbers based on which we will get the exact location. Now, each number is associated with certain properties about which we will be learning. And the first quantum number that you have to learn, the first one, please write it down. The first one is the principal quantum number. Principal quantum number. The principal quantum number is represented by small letter n. It is represented by small letter n, and the value of n can start from 1. It cannot start from 0. N cannot be equal to 0. N can start from 1 to 2, 3, 4, and so on. Okay? So when you represent the position of an electron, the first thing that you say is, what is the value of n? Is n is equal to 1? Is n is equal to 2? And when you represent the principal quantum number, what it represents? What it represents is the shell. It represents the shell in which the electron is sitting. So what do you have? You have an atom, and at the center of the atom, you have the nucleus, and surrounding the nucleus, you have many shells. This is an older model. In reality, this is not at all the case. But then, for the sake of understanding the basic concepts, just understand this concept that you have a nucleus, surrounding you have many shells, and in the shells, you have certain other subshells about which we'll be learning. And these shells are represented by certain numbers starting from 1. And each of them represent different shell. For example, let's say this is my nucleus, and surrounding this is my first shell. This is my first shell. So if my electron is sitting over here, I'll say that the value of the black colored electron, what I have drawn, is the principal quantum number value is 1 because it is sitting in the first shell. Okay. And then this is n is equal to 2 and so on. Okay, I'm not drawing it further and so on. So what we are saying is you have an atom, and inside the atom you have shell. Inside the atom you have shell. So that is the first address. That's how you start describing the address, which represents the shell of the atom. Now, if you know the value of n, there are many other parameters that you can get to know about. For example, the first parameter that you get to know about is the radius. Okay, for example, radius. So, radius of the shell. As n represents the shell number, it can also give an idea about the radius. So let's say my radius is represented by small letter r. This r is equal to n square by z, where n is the principal quantum number, z is the atomic number. And that is obvious, correct? Because as your value of n increases, for example, let's say this is the central point, and from here this is n is equal to 1. This is your radius, r1. And when you move to your second shell, this is r2, and of course r2 is greater than r1. So as your value of n increases, your radius also increases, correct? And the relation is what is represented over here as r is equal to n squared by z. R is equal to n squared by z, where z is the atomic number. Z is the atomic number. Okay, so this is one of the parameters that you get to know. Now, the next thing is, along with the radius, you also get an idea about the energy of the electron. And the energy of the electron, E, is equal to, there are various units in which you can write them, but we'll write it in electron volts. Okay, so energy is equal to minus 13.6 by n square into z square, electron volts. The units are very important. Okay, so energy is equal to minus 13.6 z squared by n. Again, z stands for the atomic number, n stands for the principal quantum number. Okay, now let's say that, let's write certain examples so that you get a better idea. Let's say my first electron is in my first shell. N is equal to 1. So we know that energy is proportional to minus 13.6 by n square. I'm not considering the z factor. I have changed this equal to proportionality just for or let's say, don't get confused. Okay. Let's say that this is my nucleus. This is my first shell. And I have one electron over here. Okay. And I want to calculate the energy of this electron, which is in my first shell. And I don't know the atomic number. Let's say I don't know because we have not learned to write the electronic configuration and all. So I'm not considering this factor of Z. So I'm changing this equal to and I'm writing it as proportional to minus 2 will be there. Minus 13.6 divided by n square. So all I know is n square and I know that they are inversely proportional. This much electron volts. Correct. So when I put this value of n is equal to 1, my energy is somewhat equal to minus 13.6 electron volts. There will be some constant along, but let's leave that. Okay. Now, next case, my electron is n is equal to 2. So what happens? Energy is again proportional. There is no change. Correct? And when you put this value of 13.6 divided by 2 square, now what is 2 square? 2 square is 4. The value that you get is minus 3.4 electron volts. Now see what is happening to the energy value. We'll use one more. Let's say n is equal to 3 and your energy value that you'll be getting is minus 13.6 by 3 square, which is 9. And it is minus 1.51 electron volt. So if you look at a scale, this is n is equal to 1, n is equal to 2, n is equal to 3, because see, this is your 0. And this is minus 1.5, this is minus 3.5, let's say, and this is minus 13.6. So as your value of n is increasing, your energy is also increasing. So don't come to this notation that 13.6, 3.4, 1.5. It's not decreasing, it is increasing. You have to consider this negative sign. You have to consider that negative sign. So as your value of principal quantum number increases, your energy also increases. And that is the reason why when you have so many shells, your electrons always tend to occupy the shell which is the closest to the nucleus. Why? Because at n is equal to 1, your energy is the smallest. And always the systems will try to occupy those states where the energy is minimum. I repeat, always the electrons will tend to occupy those systems where your energy is minimum. Why? Because energy and stability are inversely proportional. Stability is inversely proportional to energy. So if your energy of the electron is low, its stability is high. If the energy of your electron is low, your stability is high. That's the reason always the electrons first occupy the inner shells and then only moves to the outer shells. Okay, so I hope that's clear. So you get the idea of the radius, you get the idea of the energy, you also get an idea about the velocity. You also get an idea about the velocity with which it is moving. So let's say it is V. It is V and V is proportional to Z by N. V is, again, Z is the atomic number and N is the principal quantum number. All right. So there are a lot of, parameters that you can get from your principal quantum number. From your principal quantum number. And with that, we have completed our first address. First part of the address. The next one that we need is azimuthal quantum number. Azimuthal quantum number. Please note the next one. So first one was principal quantum number. Second one is azimuthal quantum number. azimuthal quantum number. Azimuthal quantum number. Now, this azimuthal quantum number is commonly represented by small letter L. Small letter L. And what does it represent? It represents the subshell. Subshell. So what did we just say? We said that if you have an atom, it has got shells around the nucleus. And inside each shell, it has got subshells. Inside each of the shell, it has got subshells. For example, if you have your, let's say your house, you have got many rooms inside and those rooms would be considered as subshells. Or let's say you have your bag inside which you have many chambers and those are the subshells. Okay, I'm telling this in this fashion so that you can just understand, that's all. Okay, so this is how you represent the second part of the address. You have to give a value for your azimuthal quantum number, and your azimuthal quantum number can start from 0 up to a value which is 1 unit less than your principal quantum number. Okay, it can start from 0 and it can go to any one value which is less than 0. For example, if your value of n is equal to 5, if your value of n is equal to 5, then the possible values of L are, you can have 0, it can start from 0, okay? You can have 0, 1, 2, 3, 4, but not 5. Why? Because it can start from 0 to any value up to n minus 1. 5 minus 1, which is 4. So it cannot have 5. Okay. Now, corresponding to each of these values of L, it has got certain notations. For example, you can draw a table out of this. Let's say your value of L is 0, 1, 2, 3, 4, 5, 6. It can go on because you can get hypothetical questions for the exam and it's important that you know. So the notation that you can use is, for 0, it's always small letter s. For 1, it is P, 2D, 3F, 4G, 5H, FGH, HI, and so on. Okay. It will go on. So these are the notations that you give corresponding to your azimuthal number. Azimuthal quantum number. What does it represent? It represents your subshell. So that's how you address your electron. So you first mention in which shell it is. And inside the shells, there are many subshells. And you tell in which subshell is the electron sitting. Okay, so let's start. Let's say that you have n is equal to 1. So the values of L that are possible is only 0. 1 is not possible. So you notate this in combination. You have 1, you have 0, and the way you notate is 1s because s corresponds to 0, correct? Now let's say you have n is equal to 2. Your value of L can be 0. Your value of L can also be 1, but it cannot be 2, correct? Because your values should be 0 to n minus 1. So corresponding to L is equal to 0, your address of the electron will be, this is nth shell. So this is 2s and this is 2p. Got it now? Next, n is equal to 3. It can have L is equal to 0, 1, 2. This is 3s, 3p, 3d. Okay, so now we have got an understanding. This is how we go. So in the first shell, you have got one subshell. In the second shell, you have got two subshells. In the third, you have got three subshells. Okay? All right. Next. So that's all about azimuthal quantum number. It will give you an idea of what is the subshell in which the electron is sitting. Next. Magnetic quantum number. Third is magnetic quantum number. So this magnetic quantum number, in certain books, they just write M, or in certain books and question papers, they might also write it as M subscript L. Okay, it's either M or ML, both represent the same stuff. And the value of M that you can have is anywhere between minus L to 0 to plus L. Okay, so till now N and L could not take negative values, but then now you can have negative values as well from minus L to plus L. And what does it represent? It represents the orientation. Represents the orientation of orbitals. So you have got a new stuff. Orbitals. So we started with atom, and then you got shell, and inside the shell we told that there are something called subshells. Inside the subshells there are some stuffs called orbitals, and these orbitals have got different orientations. I'll explain so that you can understand. Okay, let's start again. So let's say that my value of L is equal to 0. What are my possible M or ML values? Minus L to plus 1 it is, so I can have only 0, which means there is only one orbital corresponding to S subshell. I have just one orbital. I'll represent it like this. I have just one orbital, and it has got only one value, means if it has got only one value, means it has only one orbital, and the orientation is spherical. You need not learn about the orientation. I'm just giving you an idea. So the electron, if it is present in this subshell with an ML value of 0, it has got another address, another dimension, which means that it is now in an orbital which is spherical. And please understand that each orbital can have a maximum of only 2 electrons. Each orbital can have a maximum of only 2 electrons. Very important. Each orbital, please listen to my words, each orbital. I'm not talking about orbit. Orbit and shells are the same. I'm talking about orbital. Okay. Each orbital can have a maximum of 2 electrons. And I'll explain what the reason is in the next class. Now let's start with the next one. Let's say your L is equal to 1. If your L is equal to 1, you know that it is P subshell. And if it is P subshell, its value can start from minus L to plus L. And what are the values? ML can be minus 1, 0, plus 1. So corresponding to the P subshell, you have got 3 orbitals. See? So this is just one orbital, 2 electrons. Now you have got 3 orbitals. How many electrons? Each orbital can carry 2 electrons each. correct? So a total of 6 electrons. Now, in the earlier case, we said that if you have one orbital, it means one orientation. Now you have 3 orbitals, and these 3 orbitals are px, let's say, this is my x-axis. This is px. It is dumbbell shape. It is in dumbbell shape, which is oriented along the x-axis. And if it is oriented along the y-axis, it is py. And if it is oriented along the z-axis, it is pz. Okay. So corresponding to the 3 values of ml, you have got 3 orientations. And those 3 orientations are px, py, pz is how you represent it. And see, now one very important thing is you cannot say that px is equal to -1 or +1 or pz is equal to 0. No. If it is -1, it can be px, it can be py or pz. You cannot assign px as -1, py as 0. No, you cannot do that. That is not defined. Okay. So it just means that if you have your p subshell, it is always associated with 3 orbitals, and those 3 orbitals can carry a maximum of 6 electrons. Maximum of 6 electrons, and 3 orbitals will always have 3 orientations. Okay. All right. So the first one, you got 1 orbital. For L is equal to 0, 1 orbital. L is equal to 1, 3 orbital. Now next one is, let's say L is equal to 2. L is equal to 2, your D subshell. And the values are ML can start from -2, -1, 0, +1, +2. Okay. So how many orbitals? 5 orbitals. In each of these orbital, you can have a maximum of 2 electrons. Correct. So you have 5 orbitals, 10 electrons. And if you have 5 orbitals, it means that you can have 5 orientations. You need not learn them now. I'm just saying you can have 5, and those are dxy, dyz, dxz, dx squared, y squared, and dz squared. These are the 5 orientations. Okay. So for any value of L, you can find the ML values like this. Now you can try it as homework. If you try and put L is equal to 3, which is F subshell. No need for homework, let's do it. So the value of ML is -3, -2, -1, 0, 1, 2, 3. 7 orbitals, 7 orientations, and 14 electrons. Maximum 14 electrons. Correct. Now for any value of L, you can try putting it in the equation as well. For any value of L, the number of orbitals in any subshell is equal to 2L plus 1. Example, let's say I want to find the number of orbitals in F subshell. Now we know the value of L in F subshell is equal to 3. So 2 into 3 plus 1, which is equal to 7 orbitals, and that is what we have got. Okay? You can get questions from here. You need not learn, because if you know the trend, you can derive this equation as well. No problem. Okay. So that's all about magnetic quantum number, where you get an idea about the orientations of the orbitals. So we were describing about the address, right? So we started off with the shell, and then we entered deeper inside. Where we have got subshells. And inside the subshells, we have got certain orbitals. Correct? We have got certain orbitals. Now, see, this is what I'm saying, okay? If I want to pictorially represent it, let's say that this is my shell. This is just a pictorial representation, okay? And inside the shell, I have subshells. So this is my subshell. Let's say this is my subshell 1 or L is equal to 0. And I have another subshell. And let's say this is another. So you can see it is inside. This is another subshell, L is equal to 1. And there would be certain subshells which are again divided. Okay, which are again divided into orbitals. Okay, so inside the subshell again, I have got 3 orbitals. So these are my orbitals. It's not like this. This is just a pictorial representation. Let's say this is ml is equal to -1, ml is equal to 0, and ml is equal to +1. These all show my orbitals. So you can understand. Okay, so if my electron is sitting over here, you can say that my electron has got an ml value of +1, L value of 1, and shell will be 2, because without which you cannot have the value of 1. Okay, so this is where we are. Now, the last quantum number with which we'll wind up today's session is spin quantum number. Spin quantum number, which is represented by either small s or m subscript s. Or m subscript s. It's nothing. It's just the direction in which the electron is spinning. It can either spin like this or it can spin like this, either clockwise or anti-clockwise. It represents the spin. Represents the spin. And the spin value ideally of an electron can either be +1/2 or -1/2. That's all. Either in one direction or the other direction. Either +1/2 or -1/2. That's it. Okay. So I think that's enough for the session. All right. So with what we have discussed in this session, we will do some questions in the upcoming class. Okay. Yes. So based on all these 4 quantum numbers, I'll take up some previous year questions from various exams. We'll do that in the next session. And then we'll slowly move to the next topic, which is electronic configuration. Electronic configuration. Okay? All right. Bye-bye.